Good morning to all of you. So we are discussing the first unit of theory of computation, that is finite state machine. So up till now, we have discussed the basic concepts, that is alphabet, then string or word, then language, what is the meaning of language, then what is the string acceptance, how we can say that whether a particular string is belonging to a particular language or not. So that we have already discussed. Symbols, what is the meaning of symbol, how they are defined, and the string, how the string is being formed. So alphabet is nothing but one can say that. So see here, we'll just go through it. Alphabet, it is a finite non-empty set of symbol and it is denoted by sigma. It is denoted by sigma. So you have the binary alphabet comprises of 0, comma 1, or you can have all lowercase letters, that is nothing but your sigma is equal to small a, b, c up to z. You can have the combination of capital, that is lowercase, uppercase, and the numbers, alphanumeric alphabet. It is there. Then you can have string. String means it is nothing but the finite sequence of symbols chosen from input alphabet sigma. Means if we combine two or three alphabets, if you combine two or three alphabets or two or three characters, you are going to form a word, or it is also called as a string. It is also called as a string or a word, right? And if it is an empty string, if it is an empty one, then it is referred as a epsilon. It is referred by epsilon, and it is and the length of the string w, it is denoted by this sign, the length of the string. Suppose there are 6 characters, or if there are 6 alphabet in a string, x is equal to 0 1 0 1 0 0, then length of the x is equal to 6, right? Then powers of alphabet, we have already seen this. Sigma raised to 1, sigma raised to 2, sigma raised to star is nothing but your, it is nothing but the union of sigma raised to 0, sigma raised to 1, sigma raised to 2. Whereas sigma raised to plus is nothing but excluding sigma raised to 0, means without the 0 power of sigma, all other powers having their union, we are getting sigma raised to plus. Then the languages, already we have discussed. The language is nothing but the collection of strings. We can say that it is a set of all strings. It is a set of all strings over and given alphabet sigma. Over and given alphabet sigma means we have, for example, here let L be the language of all string consisting of n number of zeros followed by n number of one. And as you know that in formal language we are focusing upon the arrangement of the words, or arrangement of the letters, arrangement of the characters, or arrangement of the alphabets, and not the meaning of that particular word, right? So you can have 0 1 combination, or you can have 1 0 combination, that does not carry any meaning, but how they are arranged. So it is arranged that 0 is followed by 1, or here in this case 1 is followed by 0. So if the language said that all string consisting of n number of zeros followed by n number of 1, means n is nothing but a zero, number of zeros and number of 1 are equal in this case, and the arrangement must be 0 followed by 1. So 0 1 double 0 double 1 triple 0 triple 1. So all the strings comprising of this particular combination, such a combination, and if we collect all the strings, that is going to form your language. This is called as the language. Another language is nothing but all the strings with equal number of zeros and equal number of one. But here position is not fixed, means you can have either 1 0 or you can have 0 1. But the number of zeros and 1 are equal. So if you have 2 0, this is the combination, or this combination will also work, or this combination will also work for 2 0 2 1. Getting this point, because it is not mentioned their position. So all the strings having the combination equal number of zeros and 1, they falls under the category, or they are belonging to the language which is defined by like this. Let L be the language of all strings with equal number of zeros and 1, right? So remember this point, language. And the membership problem means we have to find out whether a particular string belongs to a particular language or not. Means we have to find out, or we have to, if the string is given, we have to identify a particular language. If the string is given to you, say for example 1 0 1 0 1 0, so we have to define the language for this. If there are the string, if the pattern of the strings is like this way in this particular manner, then we have to define the language. So it is the language having equal number of 1 and zeros. So this the way we are going to define the language, and we have to say that yes, this particular string belongs to the particular language. That is nothing but the membership problem, or that we can say that yes, it is a part of that particular language. The string is a part of the language. And already we have discussed the natural language like your English language and formal language. So natural languages is nothing but you can have the set of defined rules called as grammar, and we are mainly focusing upon the meaning or the syntax in case of your natural language like English. But in case of formal language, we are not focusing upon the we are not focused on the syntax or the semantic, but we are focusing upon the pattern, how the words, how the characters or the alphabet in that particular strings are arranged. HELLO. So these are the four characters. H is one character, E is another character, double L is another character, O is another character or another alphabet. So what is the arrangement of this? HELLO in case of natural language it has some meaning, but HELLO in case of formal language it does not carry any meaning, or we are not bothered what exactly is the meaning, but we are focused on how the letters or how the alphabets are being arranged. Because as we have discussed that in case of formal language, in case of this particular machine language, we have to think just like a machine, we have to think just like a computer, not like a human being. Getting this point? So this is the way. So the next part we have to discuss in the today's lecture is nothing but the basic machine. So basic machine, what exactly is the basic machine? What exactly is the concept? So see here, it transfers the given input to the output. Transfers the given input to the output. It is the machine which recognizes an input set I and produces an output set O, where I and O are finite. I is the input and O is the output. The characteristics of basic machine: it must has input, it must has output, it must have some states, and it must have some state relation, and it also has output relation. So basic machine, why the name it is called as the basic machine? So it is called as the basic machine because, suppose if I draw a diagram, so here is your basic machine, and you are supplying some input, to this particular machine, and you are getting output, you are getting some output. So we are only focused on the input and output part. But how exactly is the output is being produced? We are not bothered about what is happening actually inside the machine, how the machine changes its state from one state to the next state. Basic machine, that's why it is called as abstract machine. Basic machine, it is also called as a abstract machine, just like your logical gates, AND gate, OR gate, NAND gate. So all these are, so you are supplying output. Say for example, to AND gate, you are giving input, 1 1, you are getting output as a 1. You are giving input as a 0 1, you are getting output as a 0 if it is a AND gate, right? So this is the way, and how the processing is being carried out on the data supplied input, how their operations are being carried out. We are not focused on that particular thing because it is a basic machine. We are only focused, we are only means the output is only important for us, and not the internal processing, or not the intermediate states are not important for us in case of basic machine. So it is the type of abstract machine. We are not interested in what is happening inside, rather that is how output is produced, but what output is producing. So we are not questioning, we are not focused on this particular question, but we are focused on what output is producing, what exactly is the output. Suppose if you consider example of your ceiling fan, so you are changing its speed by supplying by changing the regulator knob. So initially, if it is at number one, so the fan rotates with a particular RPM. Then if you changes its speed to from 1 to 2, the speed of the fan, rotation speed of the fan increases. From 2 to 3, it again increases. So what exactly the processing is being carried out, whether it is inside the motor of that particular fan or inside the regulator, that we are not bothered about it, but we are focusing, or we are only concerned how much is the speed we require for that from that particular fan, right? So therefore this type of machine can be viewed as a function which maps the input set I to the output set O, input set I to the output set O. So this function is, remember this point, machine function always denoted by MAF. So here onwards there are a lot of machine you have to study. So we can say this is the basic machine, or this is the very primary. We can say this is the primary. It is called as the basic machine, and the machine function denoted by input gives us output. I gives you output. I goes you output means input gives you output, right? So the next we have to see the finite state machine. Then there are various other types of machines are there, and each machine is having some function. This function defines the machine. So you can easily recognize if this function is given to you, I gives you output, meaning is that input simply produces the output. We are not concerned what exactly is happening inside the machine. Remember this point, right? So examples are just like, you know, that all the logical gates like and, or, etc., the decimal to binary converter, then your electric fan, weighing machine. So you need to supply only inputs and the output is being produced. But how it is produced, that is not our concern. Our concern is only what exactly is the output, or whether this output is correct or not. Getting my point or not? Whether the received output, whether the output which we are getting, which is correct or not. So if it is AND gate, very simple example. If it is AND gate, if I AND two inputs, that is 1 and 1, so I must get an output is equal to 1. Instead of 1, if I get an output equal to 0, so definitely there is some mistake, or there is some miscalculation is happening inside that particular AND gate. So AND gate must not supply me the wrong output, it must give us the correct output. So we are only concerned with the correctness of the output, but what exactly is happening inside that particular gate, inside that machine, we are not focused on it. So though we go on increasing the speed of the fan, so fan should rotate, or fan should rotate at that much speed. But if still we are increasing the speed of the fan, and the fan speed does not get increased, so that means there must be some mistake, or there must be some problem inside that particular motor, inside that ceiling fan. Getting this point? So this is the way the output is important, provided by the given input by the user, right? Next point, or the next important machine, is nothing but your finite state machine. Finite state machine. So up till now, the basic machine is clear, that is input gives you output. But in case of finite state machine, the name itself, just be careful on the name, that is finite state machine. Yes, this is another machine, second type of slightly advanced type of machine as compared to your basic machine, and it has finite number of states. It has finite number of state, means yes, we are able to view what all the possible states in that particular machine, and these are the finite state, and we are able to see, or we are able to manipulate the states inside that particular finite state machine. So in finite state machine, the internal state of the machine alters when the machine receives an input and generates the required output. So after supplying an input, the machine changes its current state to the new state. After supplying the particular input, the machine changes its current state to new state, right? So that is nothing but your finite, and generates the required output. And yes, no doubt, yes, here also we are getting some output. But here we are not focused. Here we are not only concerned, but we have to also focus on that particular. We have to also focus on what exactly is happening inside the machine. What exactly is happening inside that particular machine. Getting this point? So it consists of pair of function. So machine function is nothing but it is denoted by machine. It has two functions, finite state machine. One is nothing but machine function, and another is nothing but your state function, denoted by STF. So machine function is nothing but your I into S. I is nothing but your set of input symbol. S is nothing but the set of internal states, and O is nothing but the set of output symbol. Internal states, input symbol, and output symbol. So in input into state, see carefully, the machine function of the finite state machine, where input into state gives you the output. In the state function, input multiplied by state gives you the next state. So this is your current state. Remember this point. This is your current state. This is the current state which gives you the next state. Means current input supplied multiplied by the current state, which produces you the, or which gives you the new state. Input supplied to the current state, that gives you the output, that is called as the machine function, and it is called as the state function. This is called as the state function. Getting this point? In case of finite state machine, so states are important. So states are important. State multiplied by input, you get output, that is called as a machine function. And state multiplied by input, if we get the next state, that is called as the state function. If we know the current state of the machine and the current input symbol, then machine function gives the output. Then machine function gives the output, and STF, that is state function, gives the next state of the machine. STF gives the next state of the machine. The behavior of such a machine can be completely determined provided its initial state and input that are known. Means you can easily determine how the machine works. You can easily determine how the machine works provided that the initial state, or the initial state, it is also called as the start state, and input, if it is inputs are given to you, if these two are in your hand, then you can easily draw the finite state machine. Means you can easily find out what exactly the next state of that particular FSM and what exactly the output is being produced by that particular FSM if these two things are known to you, that is initial state and the input. In this machine, finite set of final states. Final state, yes, there is a final state. It is also specified and denoted by F. So capital F denote your final state. Means yes, at the final state, the machine stops its execution, or machine stops there. It is called as the final state. Means there is no other state exists after the final state. So for given input, there will be only one final state. So for one input, only one final state exists in the finite state machine. The tables drawn for machine function and the state function, they are called as the state tables. The definition of the finite state machine, it can be described like this. A finite state machine, it is nothing but the model of computation. It is nothing but the model of computation. That is a computational tool to design system. It processes a sequence of inputs that changes the state of the system. It processes a sequence of inputs that changes the state of the system. When all the input is processed, we observe the system's final state to determine whether the input sequence was accepted or not. Finite state machines are comprised of the following components. The first component is nothing but the set of states. First component is nothing but the set of states. So definition says that the definition of finite state machine says that it is the model of computation. So what exactly is the computation is being carried out? So meaning is that it is the tool, or it is a conceptual tool rather than it is a practical. It is a conceptual tool to design the various system. Means you can draw a finite state machine for any known problem, or any known problem you can have the finite state machine. Say for example, if the traffic light signals are there, or if a library system is there, or if a college administration system is there, so I can have the model of finite state machine. Provided that I must know what is exactly the initial state, what exactly the current state, and what exactly input I am applying to that particular machine. Definitely the machine change, or the system, machine in the sense the system changes its current state and moves towards the next state. System changes the current state and go toward the next state, right? So that is nothing but the model of computation. So for any project, for any program, for any software, any system, you can draw the model in terms of your finite state machine. So finite state machine is nothing but, so you can have the multiple number of states. Say S1 is there, then there is a state S2, then there is a state S3, then there is a state S4. So these are nothing but the states. S1 is there, so S2 is there, so you can have S3 is there, you can have state number S4. Multiple number of states are possible in this case. And what you are applying here, you are applying input, say 0, then 1, then 0. You are applying some input. So you are applying some input here, 0. The state changes from S1 to S2. At S2, you have given input 1. That's why the state changes from S2 to S3. So what exactly the component of the finite state machine, the first and very basic component of the finite state machines are nothing but the set of states. Set of states. So states are nothing but, as the name implies, there must be a finite amount of states our system can be in only one state can be active at a time. So if S2 is there, S2 is active at a time, and you are supplying input is equal to 1. So after giving input is equal to 1, the system state changes from S2 to S3, from S2 to S3. Getting this point? The next component of the finite state machine is nothing but, or how the states are being drawn. So states are usually drawn with circles. A very basic concept. If I have to draw the state 1, so draw a circle and write the name of the state inside that circle. So S1. So I can also write like this. S1 is here. So this is my state number 1. Or I can write like this. S2 is nothing but my state number 2. Right? Initial state, the starting point of our system. Initial state is nothing but the starting point of our system. Initial states are usually drawn with an arrow being pointed to them. So this, if I draw an arrow like this, so S1 is now my starting state or the initial state. When I want to start the system, when I have to draw the FSM for a particular system, so first always it starts with the arrow pointing to S1. Then set of accepting states, a subset of known states that indicates whether the input we processed is valid or not. So accepting states are usually drawn as a double circle, means final state. It is nothing but the final state means total whether the particular string, if the string is supplied, for example, 1010, if the string is supplied to that particular machine, and if it is asked to find out whether the string is accepted by the FSM or not, if it is yes, then we have to draw the final state, and the final state always comes with the double circle. Concentric double circles are there, and it is nothing but denoted by a capital F with the circle, double circle. That is called as the final state or accepting state. It is also called as accepting state. Then alphabet, also referred to as the language, is the set of all valid inputs. So A, B, C, 0, 1, 2 means how the state changes. You are supplying some inputs, you are supplying some alphabets, you are supplying ABC as an input, or you are supplying either 0, 1 as an input to that particular system, and the state changes from current state to the next state. That's why alphabet or the input alphabets are again important part of your finite state machine. And the transitions means nothing but your state transition from current state to the next state. That is a rule indicating how the machine moves from one state to another state. So these are usually known as the two states connected by a line. So this is nothing but state 1, S1, say for example, S1 is here and suppose S2 is here, and this is nothing but your state transition. If I apply, suppose input is equal to 1. So the meaning is that at state S1, if I supplied input is equal to 1, the state of the machine, state of the FSM changes from S1 to S2. And this is called as the state transition. This is called as the transition, right? So example on the finite state machine, let us see one example on the FSM. That is nothing but your binary parser demonstration. So in case of binary parser demonstration, so let's create a finite state machine. We have to draw a finite FSM that parses a binary sequence. Means we have to parse or we have to check the binary sequence where every time we encounter a 1, we immediately encounter a 0. Means if there is a 1, after finding out 1, immediately we have to give 0. Then 1 we have to give 0. It is a valid input sequence. But if it is a 1 1 1 0 and 1 0 1 0 1 0 0, they are not the valid input sequence. Getting this point? So meaning is that if the string consisting of 1 0 1 0 1 0 1 0, then and then only this string is called as the valid input sequence. Remember this point. This is called as the valid input sequence. Meaning is that we have to see that the FSM, our FSM must check the string having sequence 1 0 1 0 1 0 only. Very simple FSM. There is no any difficulty, or there is no any one can say problem in this. Only we have to draw an FSM which takes the input as 1 0 1 0 1 0 only. If the input is like this 1 1 1 0, then it will not reach to the final state, because it is not being accepted. This particular string, it is not being accepted by your FSM. That's why it will not reach to the final state F. Or if it is the string is there, it is also, though it 1 0 1 0 1 0, but here immediately 0 comes and it invalidates your string. It invalidates your string means this particular string is also not valid. So final state will not be encountered here. and the strings, these strings are not being accepted. Only acceptable string is 1010. So how to draw the FSM? Just see here, or how to draw the finite state machine. So see here, start drawing with the state 1, S1, state S1. So three state 1, state 2, and suppose error state is there, right? And if we are at state 1, suppose if we are at S1 state and encounter a 1, because we have to see our sequence must be in this particular format, right? The sequence of the string must be in a format other, any sequence other than this 101010, that must give an error, right? The string must have this 1010 only. Other sequence, say for example 1100 or 1110 or 1100, all other sequence are treated as invalid one, right? Because we are designing a finite state machine for the sequence of this particular type 101010 only. State 1, encounter input 1, so we move to state number 2. If it is the 1 and input is 1, so go to state number S2 here. Go to state number S2. If we are at state 2 and encounter is 0, definitely we have to go back to state number 2. 0 is there, we have to go to the state number 1 again, right? At state 1 and encounter is 0. At state 1 encounter 0, we have to go to the error state, because if 0 is occur here, so definitely we have to go to some error, because it will not going to accept that particular string. Then if at state 2 and encountered a 1 here, suppose 1 input is there, so again this string is not being accepted by our finite state machine, we have to go to the error state. Getting this point? So the only sequence accepted, that is 1. So see here, this is 1 0. Again if it is a 1, so this is the way how to read this. This is the 1 0, it is again 1 and it is again 0, and this is the way. And S1 is marked as a final state, so you can have the start state and the final state same. You can observe here the state S1 is the start state, or it is the initial state, as well as it is also referred as a final state. It means it is possible in case of a FSM, the start state and the final state, it may be same or it may be different. So why it is same here? Because 1, you are giving it, you are changing its state to S2, and if you are giving 0 at state 2, you are changing the state to S1, right? But if it is a 0 here, if it is 0 here, so definitely it will not go to state 2. It will not go to state 2. It will go to some error state, right? And if it is a 1 input at state number 2, so definitely it will not go to here at S1. It will go to error state. So this is the way how to draw the finite state machine, provided with the input is equal to 1 and 0, and for the string that is 101010 only. So if we run this FSM, it will always produce you 101010 only. It will not give any other string sequence, right? The next example is nothing but the traffic lights. So if we see the example of traffic lights, so see here, a simple traffic light system can be modeled with a finite state machine. Let's look at each core component and identify what it would be for traffic lights. Means if we have to develop the finite state machine for the traffic light signals, then it must contain the states. So which are the different states for the traffic lights? Yes, the 3 states are there, that is a red signal, green signal, and yellow signal. And initially state is, suppose assume it is a green state or a green signal, right? The accepting states in the real world, traffic lights, they run indefinitely, means one after another. Initially suppose green is there, then it goes to yellow, then it goes to red, and again green and red and yellow. So there is no any final state or accepting state. And alphabet means the how much time, the waiting time for that particular signal. If it is a green signal, so how much time that the green signal will on, say for example 120 seconds or say 100 seconds, is nothing but the alphabets or input alphabet we are applying to that particular signal. Suppose the red signal, if I see the red light, so how much time that light will be there, say for example 120 seconds is the timing set for that red signal, right? So this is the alphabet, or these alphabets are nothing but your integer value, or these are nothing but the inputs given to that particular states, right? Means after 120 second only that red signal changes to the green signal, or after 100 second only the green signal changes to the yellow signal, right? This is the way. So see here, and the transitions are nothing but if we are in green state and wait for 360 seconds, then we can go to the state yellow. If we are in a state yellow and wait for 10 seconds, then we can go to the state red. And if we are at red state and wait for 120 seconds, then we can go to the state green. Suppose initial state is green state, then if we supply 360 seconds, means if you wait for 6 minutes, then you can go to the yellow light, means yellow signal will glow here. And at yellow state, you are at yellow state, and the 10 seconds you are applying, you are giving 10 seconds as input, so it will changes from yellow state to the red state. Now at red signal, all the vehicles are waiting here, and red signal, how much time it will be? It is red up to 120 seconds. As soon as this 120 second completely done or completely finished, then the state changes from red to green here after 120 seconds. So I can say that 120 seconds is the input to that particular red, 10 seconds is the input to that yellow signal, and 360 seconds are input to our green signal, right? So this is the way how to draw. This is the way how we are drawing the finite statement. So any real world example or any example can be modeled with the help of your finite state machine, with the help of the finite state machine. Say for example, I have some system. It consists of, they say for example, state number 1. Then after applying some input, it goes to state number 2. Then after applying some input, it goes to state number 3. And after some time or after applying some input, it goes to the final state. It goes to the final state. Suppose if I take a real world example like this. So this is the way. This is the way. So here is one input. Say for example, some inputs you are providing. Suppose 0 I am providing here. Then here I am providing 1. Here I am providing the 0. And after this particular S3, I'll reach to the final state. I'll reach to the final state. Getting this point? So this is called as the finite state machine. So what are the advantages of FSM as compared to your basic machine? So the question is that what exactly is the advantages, or what exactly one can say how we can compare the basic machine with the finite state machine, right? So the finite state machine, it has some memory, means it has internal state, whereas in case of your basic machine, we don't have any internal state. The machine function of the basic machine and the finite state machine, they are different. In case of your basic machine, you have just I gives you output, where in case of finite state machine, I into state gives you in the next state as well as the output of that particular finite state machine, right? And the processing power of the finite state machine is more as compared to the processing of that particular basic machine. We are comparing the basic machine and the finite state machine. The applications of the finite state machines are given listed here. Generally used in game theory, most recognized for being used in AI application. All the AI, machine learning, or you can have the data mining, all algorithms, their foundation or their basic lies in your FSM. Means you can have the states for each and every system, or each and every, we can have any algorithm you consider. For example, AI, for example, your classification or a regression technique, or if even if it is your clustering algorithms, they each and every algorithm, they have certain states, and after applying some inputs, the algorithm or that particular agent changes its current state to the next state, right? They also frequently executions of navigating, parsing text, input, handling of customers, as well as the network protocol to design some network protocols. Means you can have model, you can model anything with the help of your finite state machine. They are also applicable in vending machines, video games, traffic light, controllers in CPU, next text parsing, analysis of protocol, recognition of speech language and speeches, and natural language processing, etc. Advantages: the finite state machines are flexible because you have multiple number of states. That gives you the flexibility to the FSM. It is easy to move from a significant abstract to code execution. Low processor overhead is there, and easy determination of reachability of a state. Means you can determine key what exactly is the current state and which will be the next state of that particular FSM, right? And the limitations, yes, there are, of course, there are limitations. Means if the problem is too huge, or if it is a very large, so large problems, they cannot be drawn with the help of your FSM. Huge system, they cannot be modeled with the help of your FSM. That is the limitation of the finite state machine. So that's all about the basic machine and the finite state machine. So we have learned in this section that is nothing but the symbol, strings, the language, the formal language, the natural language, the basic machine, and the finite state machine. So hope all the concepts are now clear. And the outcome of the session is to construct the finite state machine to solve the problem. And the questions generally asked on this particular topic are define with example, symbol, strings, and the language. Write a note on basic machine. Now you have to draw the finite state machine for divisibility by three tester and draw the finite state machine for binary adder. So these problems are given. It is asked to draw the FSM for these two problems, right? The references, as always, I'm telling that always go for the good reference books. Sipsar is there, Vivek Kulkarni, Ullman is there, then Daniel Cohen, KLP Mishra. So all these are very good book of your theory of computation, as well as you can refer the NPTEL video. And of course you must refer this NPTEL video for at least theory of computation. Then there are a lot of web resources are also available on the internet, right? Okay, so let us stop here for the today's lecture. We will continue the topic in the next lecture.